Hi. Now, let's study further about this circulatory system in terms of blood vessel, physiology, and physics. So let's grasp the relationship between radius, resistance, and pressure drop, and distribution of fluid dynamics throughout our body. So first, what is blood? Blood is a circulating viscous flow in our body, which is a multi-phase, because blood is composed of not only plasma, which is a clear liquid, lots of containing proteins. However, it also contains a lot of cells, especially red blood cells. So blood is more viscous than water. So let's first start to think about viscosity aspect. Viscosity is how viscous a fluid is. You may feel that honey versus water. Let's see the actual viscosities. So the water is about 0.75 and blood plasma is about 1. And the blood is about 3 times higher than that. So, and in comparison, olive oil is about 80 and corn syrup, which is like honey, which is 8,000. So blood is a suspension of cells, especially red blood cell, which composes of almost 40% of blood volume in a protein-rich fluid, which is except RBCs, and that we call as a plasma. And the viscosity is a physical property related to resistance or to flow or deformation of a fluid. So viscosity is a physical quantity you can define as when the layer of fluid, and you imagine a plate on top while there's a wall here, when you are like pulling the plate, how easy you can pull is related to the viscosity. And more detail will be covered in fluid mechanics. So blood is now more viscous than water, or less viscous than olive oil or corn syrup. So let's understand the fluid flow, especially involved in blood flow. We call it as hemodynamics. And from our familiar circuit theory and Ohm's law relating the electrical current and electric potential and resistance, and those laws can be very similarly applied. So because network of branching vessels with decreasing diameter from aorta, which is the first artery from the left ventricle, to artery, to smaller arterioles, to capillaries. And think about the capillary. The capillary diameter is very, very small. It's approximately the same as those of cells, RBCs, within the flowing blood. Even the capillary diameter can be smaller than RBCs. So the RBC has to squeeze through to pass through. So RBCs, a healthy RBC, should be able to be very flexible. Old RBCs tend to be more stiffer, and they usually get filtered and die in the spleen. So RBCs, so capillary is really small. It's approximately smaller or the same as RBC diameter. So which is about like, let's say about order of 5 micron. So because of this, every metabolically active cells in the body, they need an oxygen and nutrient by diffusion. So they usually lie within about 100 micron of the nearest capillary for adequate nutrients for metabolism. And don't trust this number too much, because this number can vary from organ to organ. Now think about the fluid motion equation, which is coming from fluid mechanics. So as I discuss you from the system approach and engineering point of view, the fluid flow, we can apply Newton's second law, F equals ma, into this open system by defining control surface, control volume, and the pressure, which is a force from the exerting force, and the movement of fluid through inside and throughout this control surface. And you can apply this to derive fluid version of F equals ma, which we call as a Navier-Stokes equation. And that you can solve with a very simple geometry such as pipe flow. So by solving that, we will get this. This Q is a flow rate, and the flow rate is this term multiplied by delta P. Delta P is a pressure difference between. And this shape, think about it with the known Ohm's law in electrical engineering, which we know V equals IR or R times I. I is a current, or you can consider I as a charge movement, so charge flow, and equals 1/4 resistance times voltage drop. What is voltage drop or potential, which is the driving force for the electrons, electric charges to move? So similarly in fluid flow, the pressure difference makes the flow to move. So this is the driving force, and flow rate is like a current. So this term you can consider as a 1/resistance. So here the mu is a viscosity and L is characteristic length, and the R is the radius of a pipe. So if you consider this as a 1/resistance, you realize important parameter as the diameter or radius of the pipe. So resistance, in fact, is proportional, inversely proportional to the R to the 4th. This is a very important thing to notice. And what it means is the resistance is very sensitive to the diameter or radius of the vessel. So major overall resistance to blood flow, which would be the major part. And you can see those who had smallest radius will have the highest resistance. For example, if a blood flow in the blood vessel diameter is decreased by half, how much of resistance will increase, which is 2 to the 4th, it's 16 times harder to push the blood through with the given, you need for the same flow, you need to increase the pressure difference by 16 times. So this is much harder. So the flow is quite sensitive to the resistance, and resistance is sensitive to the radius. And because of that, local blood flow, eventually the blood get into the tissues such as brain or organs, and that has to be well controlled. Because of the limited blood source, you want to send it to where it's mostly necessary. So local blood flow to a tissue should be well controlled, which is done by constriction or dilation of the arterioles. Arterioles has smooth muscle cells which control this, having muscular walls, and so that it can deliver blood to the adequate place. So I put this as an asterisk, and the reason is people are arguing, asking whether is the arteriole the final controller for our blood flow, and some people argue with that. So for example, David Edwell group from University College London, they published a Nature paper in 2014. The title is Capillary Pericytes Regulate Cerebral Blood Flow in Health and Disease. So not only the arteriole, maybe the capillary self is covered by pericytes, and those pericytes might be involved in this dilation and constriction of the capillary vessel, which is the business end. So this problem is still, under a lot of debate, and people are very curious about who and what is the ultimate regulator of blood flow at the capillary level. So here we go back to the resistance is proportional 1/R to the 4th. So you can draw this, and when the resistance goes down, the radius goes down, the resistance is dramatically increased.